the cloud. So welcome everyone to today's Condensed Matter seminar. I'm Shulei Zhang, and it's my great pleasure to introduce our speaker today, Dr. Jennifer Cano. Dr. Cano is an assistant professor at Stony Brook University in the Department of Physics and Astronomy. She earned a Bachelor of Science in Physics and Mathematics at the University of Virginia in 2009, and a PhD in Physics from the University of California, Santa Barbara in 2015. She subsequently did a postdoc at the Princeton Center for Theoretical Science before she joined Stony Brook in 2018. She has received multiple prestigious awards, including the Goldwater Scholarship, NSF Graduate Research Fellowship, the Princeton John Wheeler Postdoc Fellowship, and recently the NSF Career Award and the Sloan Fellowship. Professor Cano's research is focused on the classification and the discovery of topological phases of matter, ranging from strongly correlated phases to non-interacting topological band structures. Today, she will tell us about a currently very hot topic, topological Twistronics. So without further ado, Jennifer, I pass you the microphone and the floor is yours.
Thanks. Thank you for the nice introduction, and thanks for the opportunity to give this talk. So as Shulei said, I'm going to talk about our recent work on this, we could call it topological Twistronics, which is basically applying the technology from this new field of Twistronics to topological insulators. And what we want to do is to have a new tuning knob to manipulate topological surface states. Before I get started, I will also, per Shulei's request, I will say something about our KITP workshop next spring. So next spring, 1 year from now, I'm co-organizing a extended program. It's 12 weeks at the KITP in Santa Barbara. So I think that program is called something like The Quantum Universe in a Crystal. And that cute title is meant to actually convey the fact that a lot of different types of quantum phenomena can be found in crystals. And, one of the things that I've worked on for the past several years is realizing different types of emergent particles, such as biofermions, Dirac fermions, Miron fermions. These all came from high energy physics, but we now know that these all have their analogs in crystals. And in fact, there's many other types of emergent particles that can exist in crystals that don't exist in high energy physics because there's different symmetry constraints. And so this workshop will be focused on symmetry and topology in crystalline systems. There's also a 1-week conference that everyone can apply for. And for students, the other thing I would point out is that the KITP has a graduate fellows program for PhD students. And so you can actually apply to that program. It's for a 1-semester stay at the KITP. And I think the deadline will be in the fall if you'd want to come in the spring. And that's a great opportunity to be part of this program and also just to interact with the faculty at KITP and at UCSB. So for grad students, I definitely encourage you to apply to be a grad fellow, this year or any other year if there's some other KITP program that piques your interest. So if anyone has questions about that, feel free to shoot me an email or ask questions after the talk. Okay, so now on to the seminar. So I said what we're trying to do is apply these ideas from Twistronics to the surface of topological insulators. Let me first acknowledge that this has been kind of an idea we've been working on for a couple of years with some great collaborators. So starting with Justin, Zhang, and Jed, who were previously all at Rutgers, and then moving on to the team in New York, which is my student Aaron, and G and Daniela, who are some fabulous postdocs that I've had the opportunity to work with at Flatiron Institute. Okay, so our work is motivated by twisted bilayer graphene. So twisted bilayer graphene is when you have 2 layers of graphene, 2 sheets of graphene, and they are arranged with this relative twist angle, which is very small. So that's what this video is depicting. And when this happens, the mismatch of the 2 layers creates this large scale pattern, which is called a moire pattern. And this pattern is not only aesthetically pleasing, It also can be picked up in STM measurements, but it comes along with all sorts of interesting and surprising physics that you can't find in a single layer of graphene by itself. So in particular, what's so exciting about twisted bilayer graphene is that it gives us a tunable platform to realize all these strongly correlated phases. So in these left-hand figures, I'm showing the original data from Pablo Herrero's group. And here they're realizing these superconducting domes and also Mott insulating phases. And on the right-hand side was some subsequent work from Andrea Young's group showing the quantized anomalous Hall effect. So there's all these different attributes that appear in this material, and you wouldn't find any of these things in a single layer of graphene. Understanding the nature of these correlated phases is quite difficult and definitely an area of active research. But what we know is that correlated phases come from having flat bands, and flat bands are coming because the velocity of the Dirac cone vanishes. And so we can explain this as follows. So this is a little schematic of the twisted bilayer graphene. You can see each unit cell of graphene is quite small, but when you twist with this small angle, you get this larger scale periodicity that your eye kind of sees automatically. So how can we model this? The unit cell contains thousands of atoms. Bistritzer McDonald came up with this simple model, which is that all of the low energy physics in graphene, a single layer of graphene, happens at the Dirac cones. And so if we have two layers of graphene, then we should consider how do these two Dirac cones in the two different layers talk to each other. So this picture is meant to show the K points in graphene. Each one of these has a Dirac cone, which you can see like this. And these Dirac cones will overlap with each other. And so if these Dirac cones don't talk to each other at all, then they're separated in momentum space by some distance, which is determined by the twist angle, and they'll cross at some energy, which is determined by twist angle and their velocity. But there's nothing that stops them from hybridizing. And so generically, there'll be some interlayer tunneling strength, and that will cause a gap to open when these Dirac cones hybridize. And when that interlayer tunneling strength exactly kind of matches the twist angle, then you'll get this very special point where the Dirac cone velocity vanishes and you have this flat band which is occurring between the two Dirac cones. And that's referred to as the magic angle. To be a little bit more precise, you can do some numerical simulations of this. So what this purple band is the density of states in a single layer of graphene. So that's just coming from the Dirac cone. And when the bilayer graphene is twisted at this special angle of 1 degree, then you see that the density of states changes dramatically to this blue curve. It's very sharply peaked near zero energy, which is corresponding to this flattish band here. And then it's basically zero for a little bit, which is corresponding to these little gaps on either side. So it's a dramatic change from a single layer of graphene. And on the right-hand side here, this is showing a more detailed ab initio calculation. So you should look at these black lines, which is for the relaxed atoms. And you see that there's this very flat band of bandwidth, like 10 MeV, which is appearing. So that's the flat band, which is appearing at this magic angle. It's not perfectly flat, but it has a really small bandwidth, and it's separated above and below from the conduction and valence bands. So we can think about this band by itself, and that's where the correlation physics is coming from. So in my group, we've been thinking about different platforms where we can realize interesting flat bands from Moiré physics, or as we'll see, generalizations of Moiré physics. So this is just a few snapshots of some stories that we've been working on. We've been thinking in twisted bilayer graphene. I said that there's this magic angle. There's actually a family of magic angles that get even smaller than 1 degree. And so we've been looking at the physics of the smaller magic angles and seeing that there's different types of different qualitative phenomena that appear at the second magic angle and not at the first magic angle. That's one thing that we've been looking at and looking for topological phases in those bands. And the other topic that I've been working on at Flatiron Institute is these twisted transition metal dichalcogenides. So they exhibit metal insulator transitions and magnetic transitions. And so we've mapped out some phase diagram of this and also looked at domain walls between these different regimes. But for today, I'm just going to focus on this third topic, which is how can we use moire physics or Twistronics in order to manipulate the surface states on a topological insulator. So topological insulators have gapless Dirac cones on their surfaces. So they're gapped in the bulk and have a gapless surface. And we often talk about those Dirac cones being protected, and they're protected by time reversal symmetry. And we focus on the fact that they're gapless. But actually, if you can break symmetry, you can gap the Dirac cone, and that also results in some really interesting phases. So for example, the two canonical things you might want to do, one is to break time reversal symmetry. And if you break time reversal symmetry, you'll open a gap on the Dirac cone surface, and that'll give you a quantum anomalous Hall effect. And this has been achieved. So how do you break time reversal? You introduce magnetism. And so this has been achieved in a few different ways. One is by, I think the first realization is by doping a topological insulator with chromium. This introduces magnetic moments into the system and opens a gap on the surface. So if you take thin slabs of this, then you can measure quantized anomalous Hall effect. And the other thing that you can do is break charge conservation. And this really means inducing superconductivity. And it turns out that the superconductivity you can get on the surface of a topological insulator becomes a topological superconductor. And this has kind of many exotic effects. And this has kind of launched the search for Majorana fermions. So these superconductivity on a topological insulator has been realized also in a few different ways by making heterostructures and by doping with copper. So for both of these cases, we can realize these broken symmetries by explicitly breaking the symmetry, that is deliberately introducing new elements to the topological insulator that will break that symmetry through either doping or making a heterostructure. But the question that we would like to ask is, can we achieve these symmetry broken surface states by spontaneously breaking symmetry instead of explicitly breaking it? So this would save us the effort of either doping our system, which creates a lot of disorder, or of making a heterostructure, which requires kind of very specific material constraints, trying to think of different layers that will be epitaxially matched so they can have electrons tunnel seamlessly between them. So we want to know, can we have spontaneous symmetry breaking on the surface of a topological insulator? So this question is not, I'm not the first person to ask this question. So I think starting from around the discovery of topological insulators, which was around, say, 2010, people have been trying to search for these symmetry broken phases. And so I'm just showing one picture here, one plot from this paper, where they're looking for ferromagnetism on the surface of the topological insulator. And so what they're plotting here, the x-axis is a function of the velocity of the Dirac cone, and the y-axis is the strength of the Coulomb interaction. And so what's being shown is that we have the surface Dirac cone for small Coulomb interaction. And if you cranked up the Coulomb interaction, you would cross a critical interaction strength where you would gap out the Dirac cone, and this would lead to surface magnetism on the TI. And so on this plot, they marked bismuth selenide and bismuth telluride, and note that the plot doesn't go down to zero. Zero would be around here. So these are actually these two materials, which are the two most well-known TIs, are pretty close to the critical interaction strength, but not high enough. And so we wouldn't expect spontaneous symmetry breaking in these materials according to this simple calculation, because the Coulomb interaction is not strong enough. And this agrees with the experiment that we don't observe spontaneous ferromagnetism on the surface of a TI. So how could we reach this? Well, one thing we could do is to consider topological insulators that are made with more correlated atoms. But the other approach, which we're going to take, is instead of increasing the Coulomb interaction, can we increase the density of states in some way? And the way that we want to do that is by applying Twistronics. So I showed you in graphene how the density of states of graphene gets severely enhanced by twisting the two layers. And so the question is there some similar thing we can do to the TI surface that will increase the density of states and thereby push us into this regime of gapped, spontaneously broken symmetry surface states? So I have a few different platforms in mind to achieve this goal. So I'll introduce them kind of in order from least accessible to most accessible. So first, we were thinking of these different types of twisted heterostructures. So my first idea was, why don't we take two different 3D TIs, these are 3D slabs, say, stack them on top of each other and arrange those with a twist angle. So we're kind of making a 3D version of twisted bilayer graphene, but out of, say, bismuth selenide. So at the interface between them, we'd have these two different Dirac cones, and maybe these things would behave similarly to the two Dirac cones in twisted bilayer graphene. So we thought about this approach, and I'll explain it at the end if there's time. And the bottom line is that we can get magic angle conditions, but there's a few caveats. And in addition, I'm not sure about the feasibility of this heterostructure because these TIs are really 3D, not 2D materials. So I then turned my attention to what I think might be a more reasonable heterostructure. Now, of course, I'm a theorist, so people can pipe up whether they think it's reasonable or not. But this next idea is, what if we put a 2D layer on top of our 3D TI, something that's kind of lattice matched, and then twist those? And so that will, that seems like a little more feasible to me because this 2D layer maybe could be more easily twisted than these 3D materials. And so this is actually what I'm going to describe in a lot more detail. But the bottom line here is that the effect of making some heterostructure like this is that the 2D insulator, if this is an insulating material, it will impose a potential on the TI surface. And if these two materials are very closely matched but mismatched, this will create our moire pattern, and this potential will be some slowly varying potential on the TI surface. And the basic result that we find is that this setup doesn't realize a magic angle, but it has two main effects that I'll talk about, which is that it renormalizes the velocity of the Dirac cone, and it also introduces a Van Hove singularity that can drive magnetic surface states, which is kind of what we're after. And then finally, there's a third idea, which I really like, which is, what if we take our 3D TI and put it on top of this setup? So we take some dielectric material and punch a bunch of holes in it in a regular pattern, and then put a gate underneath. And so that way the 3D TI surface will feel the gate in a spatially modulated way. And that will also have the effect of having some long, large scale potential on its surface. And so these two approaches, physics-wise, experimentally wise, are very different from each other. But theoretically, they're kind of doing the same thing, which is they're imposing a periodic potential on the surface of a topological insulator. And what I like about this second approach is that there's a lot more tunability because you can change the spacing of this dielectric, you can change the Bravais lattice, and you can also change the potential that you get from this gate. Versus in this setup, once you pick your materials, all those things are fixed. There's not much tunability except for the twist angle. Okay, so those are the platforms that I have in mind, and I'm really going to be talking about these two setups, which map to the same problem. And like I said, maybe there's 5 minutes at the end where I can briefly describe this other setup. So, right, so I'll talk about these setups that I just described and show you our perturbative results and then some numerical results, and then finally get into this point of how interactions can drive a magnetic spin density wave on the surface. Okay, so what happens when you put this super lattice potential? So that is, just think about some potential which is modulated in space, but not just in one direction, but in both directions. What happens when you put that on the surface of the TI? What that potential does is that it breaks translation symmetry. So your TI surface has this Dirac cone. Every point on this Dirac cone is labeled by a momentum K. We're used to K being a good quantum number, but if you break translation symmetry, different K points will couple to each other. And so what happens is that the different K points that are separated by the wave vectors of the potential, those points will be coupled. And so this has the effect of folding the Brillouin zone. And so our very nice looking Dirac cone that I've shown on the left-hand side turns into this folded Dirac cone on the right-hand side. And so originally the density of states would also be a sharp V shape. But what happens now is that the density of states develops all these ripples, and these ripples can be traced exactly to what's called satellite cones, these different points in the energy spectrum where you see that there's like new Dirac cones that are emerging. Those gives you these dips in the density of states. And so if you can measure the density of states of this heterostructure in these dips, then that would tell you something about the Fermi velocity of your material, and it would tell you, it would kind of confirm that you've achieved, that your potential is actually affecting the Dirac cone in the way that you expected. So the main effect of imposing a superlattice potential on this Dirac cone is you get these satellite cones that I've described. What the other effects are that you change the Dirac cone velocity. So basically, because you keep folding the Brillouin zone and then opening gaps at the corners, you end up changing the velocity of the Dirac cone. And that's the way that we're going to increase the density of states, which, remember, was our goal here. And the other thing that I'll talk about is that this also introduces Van Hove singularities at the corners of this new, of the new smaller Brillouin zone. So those are the main effects of having the superlattice potential on the TI surface. And I'll discuss, I'm now going to discuss these things in a little more detail. So, so the first effect that I mentioned is that the superlattice potential changes the Dirac cone velocity. That's what I mean by renormalizing it. So we can ask the question then, using perturbation theory, how much does the velocity change? And this is kind of akin, you know, and on my second slide, I had a picture of these two Dirac cones in twisted bilayer graphene, showing that there's some critical tunneling strength where you get this magic angle and the velocity goes to 0. You can compute that magic angle to first order in perturbation theory. So we're now going to use that same type of perturbation theory to the surface of our TI to see how much does the Dirac cone velocity change with the potential. So perturbatively, we find the following thing, that our Dirac cone velocity is proportional to the original velocity, but there's this factor in the denominator that goes like 1 plus alpha. And so this parameter alpha I wrote here, let me say something about it. In the numerator is the strength of the potential. So as you make your potential strength bigger, then the velocity of your Dirac cone will get smaller. And in the denominator is the wave vector of the potential. So as you make your length scale bigger, which means your wave vector is smaller, this parameter alpha gets bigger, and then your velocity gets smaller. So those are two different ways that we can get a new velocity of our Dirac cone. And this is actually pretty analogous to twisted bilayer graphene. Increasing the potential strength is akin to increasing the interlayer tunneling strength, and making the supercell bigger is akin to making a smaller twist angle. And both of those things will decrease the velocity in graphene. However, there's a big difference here, which is that you can see from this functional form that this will never go to 0 because it's like 1 over 1 plus alpha. So that function never goes to 0 or any value of alpha. And so in this system, then, we will never realize magic angles where the velocity disappears. Instead, we'd expect that there's some slow decay of velocity, which will start approaching 0 as long as this perturbation theory is valid. So that's just leading order in perturbation theory, and you might not trust it very much. We ourselves were a little bit skeptical. Does this actually describe what's going to happen in a real system? And so there's a couple things you might worry about. One is that we only use this continuum model of a Dirac cone. So we just said perfectly linear, goes on forever that way, but it ignores any sorts of ripple effects or what's called hexagonal warping of the Fermi surface in bismuth selenide. And the other thing is that it completely ignores any bulk physics. It's just talking about the surface physics. And so in order to address both of these things, I'm now going to discuss our numerical results, which are for 3D bulk lattice models, which they're in a slab configuration. So they have surface states and bulk states, and the surface states are not going to be perfectly isotropic. So this will give us a modification on our perturbative results. So the first model that we're thinking of is this idea that I mentioned of having a 2D insulator on top of a 3D TI and twisted. And so there's going to be, so we think of a Hamiltonian, which has a TI Hamiltonian, a 2D Hamiltonian, and some coupling between them. And if there's some, you can make some kind of basic assumptions of translation invariance on this coupling. And then you'll see that the coupling can be Fourier transformed in this way. But the important point is that this is why I want this 2D layer to be an insulator. If it's an insulator, that means we can actually integrate out the degrees of freedom in the 2D material. Or to say it differently, an insulator is inert. And so the only effect of this layer on top is to create a potential on the TI surface. And so formally, we do that by integrating out these fermions coming from the 2D layer, and we can actually compute, if we knew what the interlayer coupling was, we have a functional form for what this effective potential would be. And of course, that's going to depend on your material choices, your twist angle, your lattice mismatch, all of that stuff. So to be very concrete, we consider a square lattice, which is, we take a 3D TI model, which is called the Bernoulli-Hughes-Zhang model. It's just the kind of canonical model of a 3D TI. And we put a potential on its surface. So just on the top layer, it's 3D slab, and we have this cosine potential on its top surface. And we chose this kind of weird form for the potential because it's the potential that would result from integrating out this 2D insulating layer on top. So these are just kind of details. But I just wanted to show them to be concrete, to show that we're thinking about a very concrete model that we just put on the computer. And so the results that come out are as follows. So this is, let me explain what this plot is. This is a plot showing the velocity of the Dirac cone as a function of the strength of the potential. And so recall from the perturbation theory that I was just showing, that if the potential strength gets bigger, then since it's occurring in the denominator, velocity should get smaller. And so this is exactly what this plot is showing. So these dotted lines are all different numerical simulations, or these dots rather. They're all different numerical simulations as we're increasing the potential strength. And this solid line on top of it is our perturbation theory, but it's actually perturbation theory going out to 5th order so that it stays valid for longer. And you can see that we capture this general trend, which is as the potential is getting bigger, this velocity is getting smaller, and eventually it starts to nosedive. And then the perturbation theory keeps going, but numerically it shows that there's some minimum and it starts coming up. So this is rather neat because we've achieved a pretty significant renormalization of the Dirac cone velocity down to around, say, 0.3 or 0.4 if its original value. And these other plots are showing those satellite cones. We can also track their velocities, but we're not going to do anything with those for today. So the main point is that our numerical results back up our perturbation theory that we can change the velocity of the Dirac cone by applying a superlattice potential. And we can also plot this in a different way, which is keep the potential strength the same, but change the wave vector or change the length scale. And so now same thing, each one of these dots is a different numerical simulation as we're changing the wave vector Q. And the lines are showing our perturbation theory. And so they trace out each other pretty well. And again, what we can see is that we can change the Dirac cone velocity at least down to half of its original value by changing the length scale of this potential. And it seems like this plot could keep going down even more, but it became numerically unfeasible to consider larger system size than this. So I think that this platform offers us a great degree of tunability in changing the Dirac cone velocity. So that's just our toy model. So what we next want to do is apply this to actual, some real material. And the problem is that, remember, this setup is having a 2D layer on top of a 3D TI. And so the big problem that we encountered is that in order to get these this very small lattice mismatch to create the moire pattern, it needs a very good choice of material, and we didn't have such a good choice. So the basic problem is that if your mismatch is too big, then your the resulting wave vector Q of the moire pattern is going to be too big, and you're going to start coupling surface states to bulk states, and that's going to have some very different physics. So we want to keep that wave vector very small so that we can just couple the surface states. And so that led us to this alternate approach that I was talking about. Instead of putting a 2D layer on top of the 3D TI, we can think about having this pattern dielectric, cutting holes in it, putting a gate in top, and now the potential from the gate is only going to hit the TI in this spatially modulated way. And so that's a very controlled way to adding a periodic potential. And I should mention that this idea of adding a periodic potential by this pattern dielectric, it was realized experimentally by Corey Dean's group in this neat 2018 paper. They did this on graphene. And so just to throw some numbers out there, the lattice spacing, so the unit cell of this pattern, they got as small as 35 nanometers, and the potential strength got up to 50 MeV. So that's roughly the order of magnitude, which is state of the art. So we now want to model this periodic potential on the surface of bismuth selenide. So how do we do this? We do an ab initio calculation. So we make a slab. Our slab is consisting of 5 quintuple layers. And so these gray lines that you can see, the gray is from our ab initio slab calculation, and these red lines are from our von Neureis type binding model. So at higher energies, they don't match each other, but we're interested in the low energy physics of the Dirac cone. So zooming into this physics around the Fermi level, you can see that the Dirac cone is very well captured by our type binding model. And so we use this type binding model to figure out what are the orbitals that have weight on the surface. So if we apply a potential on the surface, what are the orbitals that are going to feel that potential? And so then that's exactly what we do. We take this type binding model and we add a spatially modulated potential. And in our case, for the results I'm going to show, we consider this, the length scale to be around, I think, like 11 or 12 nanometers. We picked that because that was the length scale of twisted bilayer graphene. So we thought that that might be a good length scale to consider, even though it's a bit smaller than the currently accessible dielectric patterning, like I was showing from Corey's group. So when we impose that periodic potential on the TI surface, what we see, so this is again a plot of Dirac cone velocity versus potential strength, but now it has real units because we're thinking of a real material. You should look at this red curve. These red dots are again different numerical calculations, and each one of these is occurring at a different strength of this potential. And you can see that as we turn up the potential strength, the velocity of the Dirac cone dives down again. And kind of the interesting thing to me is that similar to our toy model, it reaches a minimum, which is around, say, 1/3 of its original value, and then it comes back up. So we see again that by applying the superlattice potential to the TI surface, the Dirac cone velocity can be significantly changed to roughly 1/3 of its original value. And I want to emphasize that this is actually a pretty big change because if the velocity is going down by a factor of 3, then the density of states, which goes like 1 over velocity squared, will go up by almost a factor of 10. So that's a non-trivial change. And if we return to this plot that I was showing before, remember this is interaction versus square root of velocity. This is showing us the critical interaction strength needed to gap the Dirac cone. If we change velocity by a factor of 3, this pushes bismuth selenide and bismuth telluride way over. And it looks, in fact, like bismuth selenide might be above the critical interaction strength predicted by this calculation. So this renormalization by a factor of 3 might be enough to realize a gapped magnetic surface state. Okay, so I think that this superlattice potential offers neat opportunities to tune the surface Dirac cone. And there's another thing that I wanted to talk about, which is that, so previously what I've been talking about is changing the Dirac cone velocity. So that is taking the Dirac cone and flattening it out a bit in order to increase the density of states at the Fermi level. But the other thing that happens from having this superlattice potential is that you introduce Van HoveSingularities, and these Van HoveSingularities are not at the Fermi level, but they're above the Fermi level. And so, so let me say something about this plot. These dashed lines are showing the original Dirac cone with its linear dispersion. Now we apply a superlattice potential, maybe by this method that I was describing with the pattern dielectric, and we get this new band structure, which is the red and black solid lines. And we see that they're not perfectly linear anymore. There's this flat spot And that flat spot is a Van Hove singularity, and it leads to a pileup of the number of electron states. And so this plot on the left is plotting density of states as a function of energy. And so you see that there's a peak in the density of states exactly corresponding to these flat spots in the band structure. And so this is another way that we can increase the density of states, not at zero energy, but at some higher energy. So these Van Hove singularities can also kind of increase the effective strength of the Coulomb interaction. And since they're located near the K and K prime points, so not at the gamma point, they're going to drive some kind of density wave. And what happens for our topological surface is that it drives a spin density wave instead of a charge density wave. The reason is because this is a little sketch of the TI Dirac cone. As you move around on the Dirac cone, as you move around in momentum, spin also moves. So spin and momentum are locked. That's the unique property of Dirac cones on the surface of topological insulators. And so if we have these Van Hove singularities at the K and K prime points, the spin at each of these points is going to be moving. And so coupling these different points to each other is going to be coupling different states that have different spins. And so naturally, a spin density wave is the natural instability that you would expect. So what we did was look for a spin density wave instability of the following forms. This is just some kind of magnetic order, but the wave vectors that appear in here are exactly the vectors that are separating these different Van Hove singularities. And so that will determine the periodicity of the spin density wave. And I want to emphasize that this thing is tunable, the spin density wave, if it does have an instability, it's tunable. Its length scale is tunable by changing the length scale of this periodic potential. So that's another neat feature that comes out of this. Okay, so to be concrete, this is what we computed. We have our Dirac cone, we have our superlattice potential, and we have the Coulomb interaction, which we just treat as an on-site Hubbard type interaction. We take it to be repulsive from electron-electron repulsion. And then we look for a magnetic order parameter that's going to minimize the total energy of the system. And that magnetic order parameter is subject to the constraint that spatially it's modulated. And those spatial modulations are determined by the distance between these Van Hove singularities. There's actually a large space of such parameters because there's three different possible wave vectors. And there's also, for each wave vector, 3 different spin orientations, which is like parallel, perpendicular, or out of the plane. So there's in total a 9-parameter space, and we're trying to find what's the order parameter that in that large space of possibilities that will minimize free energy. And so the result that we found is actually even more surprising than we imagined. The resulting spin configuration that minimizes the free energy it forms what we call, or I think what's called, a Miron lattice. So let me say something how this works. So first off, remember what a skyrmion is. So a skyrmion is if you have a ferromagnet, say all of your spins are pointing downwards, and say in the middle you have one spin up, then that spin up will be some kind of defect, and it'll, as you go away from the middle, it'll smoothly interpolate until it points down at the boundaries. A Miron is half of that. So it has a spin up at the center, say, but its boundaries are all pointing in plane, or it has a spin down at the center and its boundaries are all pointing in plane. So it's like half of a skyrmion. And so that's exactly what, this is our numerical solution. That's exactly what we see here. So the color in this plot is telling you about the Z component, or the out of plane component of spin. And the length of all these arrows is telling you about the in-plane component. So like here, what we see is that we have a spin, which is, say, pointing out of the plane, and then it smoothly interpolates around to the boundary where the spins are pointing pretty much in the plane. And then you move to another unit cell and it's pointing into the plane. And then again, smoothly interpolates to a bunch of spins that are pointing in plane. And so each one of these things is a Miron, and they form this super lattice. So each hexagon is a unit cell of our potential. So remember, we applied this spatially modulated potential. It has a periodicity, and these hexagons tell you that's the unit cell of that periodic pattern. The magnetic order forms a larger supercell where 1 out of every 3 cells is a Miron of one orientation, 1 is a Miron of the other orientation, and 1 is kind of empty. So this is a rather unusual pattern. And it's also pretty unusual because Mirons don't occur very often in nature. Skyrmions occur more often because they have a quantized topological invariant, but Mirons don't have that property. But this system has a lot of extra symmetry. And so what happens is that along these certain mirror planes, the spin is actually always pointing in plane. And so that's actually, I think, what stabilizes this Miron lattice. And if we compute what's called the Pontryagin number, which is basically the Skyrmion number, we see that it's actually quantized to be +half and -half in all of these different triangular regions. So these things are really like half Skyrmions that are interspersed with each other in just the right way to be stabilized. And so I think that this pattern is a compromise between electrons want to sit in the minima of the potential, but they also want to have the spin momentum locking from their kinetic energy. And so this pattern has a little bit of both of those things. Now, I mentioned earlier that for ferromagnetic order, the surface of the TI would be gapped, and you can measure quantized anomalous Hall effect. But here, the surface remains gapless because there's a lot of symmetry preserved even with this magnetic order. And so we see that there's not a full gap that opens on the surface, but the density of states does split. That's what makes this reduce the total energy of the system. And so this rather weird order results in a gapless magnetic surface state. And finally, the other interesting point to make is that from our calculations, we think that this Miron lattice could actually be within experimental reach. And so, for example, so this is a plot which is showing if we estimate the Coulomb interaction to be 30 MeV, what's the critical temperature of the spin density wave? And so we see that the critical temperature can be as high as a few Kelvin. So that's something that can be experimentally measured. And to give you some feeling of where the peak of this phase is, so the x-axis is W is the strength of the potential, VF is the Fermi velocity, and L is the length scale of the potential. So if we chose a length scale of 10 nanometers and a potential of 40 MeV, that's one way, taking the velocity of bismuth telluride, that we could lie pretty much at the peak of this plot where the spin density wave is the strongest instability. But there's also other combinations of length scale and potential strength that would also put us at this peak. So if the superlattice is bigger, then the potential can be smaller. And that might be a little bit more feasible. And then the second plot is showing kind of the inverse. Each one of these lines is a different temperature, and it's plotting the critical interaction strength needed to realize the spin density wave at different temperatures as a function of filling. And so the smallest critical temperature is exactly at, say, the 2/3 filling, which is where these Van HoveSingularities are. But at other fillings, you can still realize this phase. And as you go to higher temperatures, then a larger interaction strength is needed. Okay, so this is kind of the main result, which is that, well, I guess there's two kind of main results. One is that the superlattice potential can significantly change the Dirac cone velocity. And the other is that the superlattice potential creates this Van Hove singularity at 2/3 filling, and that leads to a magnetic instability, which is this exotic Miron lattice. So maybe I'll just spend, say, 5 more minutes to talk about the other setup that we originally were thinking of, which is what happens at the interface between two different 3D TIs. So this is, I'll just go through this very quickly because it's, I think, a little bit further from experimental reach. I'll explain why. So the last part is this idea: what if we took 2 3D topological insulators and made a twisted device in that way? At this interface, we have 2 Dirac cones. And so you might think that the physics would be very similar to twisted bilayer graphene. But the problem here is that in the 3D TIs that we know, their Dirac cone, like bismuth selenide and bismuth telluride, their Dirac cones are at gamma. And so if you twist these 2 layers, then there's no offset. And so you don't get flat bands like this. You would just open up a band gap. So what we end up doing, again, as theorists, we can do this. We can consider a fictitious topological insulator. We don't have any material in mind, and its Dirac cone, instead of sitting at the origin, will sit at the boundary of the Brillouin zone. And so that way, when we twist the two different layers, the Dirac cones acquire an offset in momentum space. So this is some picture of that. And for the square lattice, we twist these, they get shifted from each other, and then they have this little momentum mismatch between them. And in this case, we follow out, we do the perturbation theory, just like we did before, to find the Dirac cone velocity. And we do see that there's a condition for magic angles, which is where the velocity vanishes. But that only occurs if your interlayer hopping has a spin flipping term. We can kind of understand this because if we think of these two Dirac cones where they cross, their spins will be pointed in opposite directions. So in order to open up a gap between them, we need to have a spin flipping interlayer hopping term. There's an analog for this in twisted bilayer graphene, which is in order to open up a gap, you need to have a sublattice flipping term. But in twisted bilayer graphene, that's fine. There's no reason that you shouldn't have A, B interlayer hopping. But here, having a spin flipping term is a little bit more unusual, although it is allowed by symmetry. So then we need to make another assumption if we want to go further, which is we need to assume that we have such a term in our 3D TI interface. And so if we do that, we can compute the band structure. And so these different plots are turning up the interlayer hopping. And we see that there's some critical hopping where we start getting these really flat bands that appear, but they're not decoupled from other bands. And so it's not nearly as ideal of a system as twisted bilayer graphene. And so this is showing our, this red line is our, is the results from these numerical simulations. So as we turn up interlayer hopping, the velocity gets smaller and smaller. And then this red dashed line is our perturbative result, which shows that there is a magic angle where velocity vanishes. But in our simulations, we never actually see that. If we don't include the spin flipping interlayer hopping, then we never see really flat bands. So this is kind of the flattest that the band structure gets. There's nothing really flat in here. And that's what these black lines are showing. The velocity never approaches zero. So we don't consider this to be a very promising platform to realize flat bands on the TI surface. So we tried to then consider what if there's a more realistic platform, and that would be graphene on bismuth selenide. And so, so graphene and bismuth selenide are actually kind of closely lattice matched, off by a factor of 3%. And so we pretend that it's actually supercell matched, not perfectly matched. So you can see that the TI lattice, which is these blue atoms, is a factor of 3 bigger than the graphene lattice. So we pretend that they're perfectly superlattice match and then twist them to create this momentum mismatch or moire pattern. And then we can repeat the same calculation for graphene on the on bismuth selenide and ask, can you get magic angles? And again, what we find is that the only way to get a magic angle is to have a spin flip when it hops from graphene to bismuth selenide or back. And we, that term is physically allowed. It will probably be present, but it will probably be very small. I don't see any physical reason why it would occur. So again, I don't consider this to be a very promising platform to manipulate the velocity of bismuth selenide. So, okay, so this is my last slide. I want to just summarize the 3 things that I've shown you. The first part was showing how if we apply a superlattice potential to the surface of a topological insulator, we can significantly change the Dirac cone velocity by, say, a factor of 3, and this will enhance the instabilities towards correlation-driven physics. Then I said, well, how about if we move away from zero energy, but move up higher in energy? There's actually Van Hove singularity that results from this superlattice potential. And that also drives a different type of instability. And that leads us to this kind of exotic Miron lattice. And then finally, we considered this interface between 2 3D TIs, and we showed that there is a magic angle condition, but that the magic angle requires having somewhat unrealistic spin flipping terms. And so out of these different possibilities, we consider the most exciting prospect to be applying the superlattice potential to the TI surface and potentially realizing different types of magnetic surface states. So with that, thank you for your attention. I'd be happy to take any questions.
Thanks, Jennifer, for the very clear talk. And I like the ideas with twists. The talk is now open for questions. Any questions from the audience? Okay. Harsh?
Sure, yeah, that was a really nice talk. A lot of really interesting work. I had a very superficial outsider question, really, which is, sometimes you've used this criterion that if the velocity vanishes, that's a flat band. I guess my question might be partly sort of sociological, is that considered an acceptable criterion for flatness of the band? And I guess the other remark was just that if it's just one parameter that's vanishing, it's sort of easy to imagine tuning it. But I thought, if you wanted to get the band flatter than that, that would be like something that would require magic. So I was wondering what your thoughts are.
Yeah, no, this is a great question. So actually, I can go all the way back to the beginning, which is this twisted bilayer graphene, right? Exactly. So this is kind of my simplistic explanation. What you're really showing here, what you can compute using perturbation theory, is that velocity vanishes. Now, velocity is only the linear term in the dispersion. So that's not the same thing as having a flat band, not at all. And what you see from these sorts of plots, so what these are doing is saying, suppose it's still a simplification. It just says that you only consider Dirac cones and you couple them to each other based on this twisting. But what you see is that it's kind of hard to see from this plot, but the velocity at this magic angle might be flat in some directions, but it's not a completely flat band. There's still a dispersion, and this density of states is not diverging as it would from a flat band. It's just producing some peaks here, and these are coming from Van Hove singularities. So it's definitely true that this band is called the flat band, but it's not completely flat. And vanishing velocity is just the vanishing linear term in the Hamiltonian. So it does not force the entire band to be flat. And I'll just say, in case anyone is interested, there is this special fine-tuned model for twisted bilayer graphene, which only involves A to B interlayer coupling, no AA. And in that model, you produce literally flat bands, and you can show, that's called the chiral model. You can show that, you can show analytically that those bands are flat, and it has kind of some special symmetries associated with it. But in general, we don't expect these bands to be completely flat, but we call them flat bands anyway, because they're still pretty small.
Thank you.
Walter? Walter, do you have a question?
I think you're muted, Walter. Walter, you're muted.
Okay, sorry. I was a little flabbergasted. I thought you were going to ask Mandela first, but anyway. So I had sort of two questions. I mean, to me, flat bands is, well, flat compared to welt, right? So it's the bandwidth compared to a Coulomb interaction. And
Correct.
Is there anything one can do on the other end of, controlling the Coulomb interaction? And yeah, so and the other question is, well, once you are in the regime where the Coulomb interaction is bigger than the bandwidth, then, how do you distinguish these different things that can happen? You can have multi-insulators, you can have this superconductivity, which maybe has something more to do with the spins and so on. So can you say anything about generic things that one can deduce from these models of what would happen?
Yeah, so, well, first of all, just to answer your first question, although I think you kind of answered it yourself, but just to make it clear to the rest of the audience, flat is always compared to the scale of Coulomb interaction, and your Dirac cone originally is very much not flat because it's linearly dispersing over a range of a couple of EV. So that's the opposite of flat. When we make these bands, which have a scale, a bandwidth of say 10 MeV, now apparently that's more susceptible to the Coulomb interaction. So, okay, so flat is always a relative statement, and it always means relative to Coulomb. And certainly you could consider making, say, a version of graphene with heavier elements, and maybe that thing you wouldn't need to have flat bands in order to realize correlated phases. Okay, so the next question is really the subject of the whole field, which is how do we know there's many different types of correlated instabilities that can occur? And the thing about this system that I think is what has made it attract so much attention is that it basically realizes almost all the correlated phases that you could think of. I mean, you know, these phase diagrams are quite rich. You know, part of that is because you can tune twist angle and you can tune carrier density. And in addition, you can change the symmetry a little bit by depending on the substrate that you put the whole system on, and you can also apply a magnetic field. And so I think that theoretically, it has been incredibly difficult to make a precise quantitative prediction for what is the correlated phase that's going to occur. In fact, I don't really think that that exists. But what has been able to be done is kind of consider different simplified models, and that gives some intuition. So I think superconductivity has been very speculative, but I think we now understand better quantum anomalous Hall. And that's actually this chiral model that I mentioned. It's a simplified model, but it actually reduces down, it reduces everything down to its most simple elements, I think, which is it creates flat bands, and those flat bands are actually sublattice polarized, and they have a Chern number. So they will give you quantum Hall effect if they weren't degenerate with each other. And so when you put this whole system on hexagonal boron nitride, it breaks sublattice symmetry. So that already splits one degeneracy. And then you just need some kind of spontaneous time reversal symmetry breaking to split another degeneracy. And that's how you get quantum anomalous Hall. So that chiral model gives you the right basis to use to understand quantum anomalous Hall. I think the other types of phases are totally up in the air. And actually, depending on the theoretical tools that you use, I think you could probably get different results because different methods have different biases. So I think the theory has been all over the place, and we are now just emerging on some themes of breaking sublattice symmetry helps the quantum anomalous Hall emerge. Actually, that's kind of the only theme that I really know of here. I don't think people understand the nature of superconductivity, and they don't really. There's probably been some proposed correlated insulators, but I don't think there's a consensus on exactly the nature of those things either. So the theory has been really hard, and the interested bilayer graphene is driven by experiment, I think.
Thank you. All right, next, Mandela.
Thank you. And thanks for the nice talk. So I had sort of a general question about the magic angle itself. I think you mentioned that it's sort of measuring the distance between the Dirac cones, right?
Mm-hmm.
So I was like thinking, so in a Weil semi-metal, you have this axion, which is sort of this space-time dependent axion, which is sort of measuring the distance between the Weil nodes. I was wondering if there's like some analogy there. And if so, like, could you have like a space-time dependent magic angle? Would the rate of change of the magic angle itself have any physical significance?
That's a hard question, I think. I think that it depends on what you allow yourself to tune. And so to me, there's not an obvious way. If you have some Weil fermion material, the Weil fermions kind of are where they are. And of course, you can move them around by, say, applied field or pressure, but there's not a great degree of tunability. And what makes these 2D materials so neat is that they are so tunable. Nonetheless, you can still add some term to the Hamiltonian or make some toy model that has this feature that the Weil cones are very near each other. And probably you can also create these vanishing velocity. I don't know what the consequence of that would be. Maybe also give rise to correlation driven physics. And I don't, yeah, the rate of change of that thing, yeah, I haven't thought about that. I'm not sure what that would bring.
Okay, thank you.
Okay, next, Reha.
Yeah, I have like two naive questions. So the first one goes back to what you mentioned at the beginning. So why does the increase of the density of states lead to this magnetic phase transition?
Yeah, so I guess I'm not sure which slide to go to, but basically, the spontaneous symmetry breaking is driven by Coulomb interaction. And you can think of the Coulomb interaction as being an electron-electron interaction. And so the more electrons that are packed into a tight space, then the stronger that interaction is going to be, and the stronger this effect will be. And so if you have a peak in the density of states, that's telling you that there's a lot of states in a very small energy window. So that means there's a lot of electrons which are kind of crammed nearby each other. And so those things are going to be more susceptible to being split by the Coulomb interaction. And I guess it's similar to the question about flat bands. You don't actually need a flat band to have instability to Coulomb interaction. What you really need is a peak in the density of states. And you want the width of that peak to be on the scale of the Coulomb energy. And when that happens, then what the Coulomb interaction wants to do is split that peak, and that will save energy because it'll be like two smaller peaks. One will be occupied and one will be empty. And that thing will ultimately lower the overall energy of the system. Does that answer your question?
Yeah, thanks. My second question is, like, do you expect superconductivity to also exist in this system? And if not, is
right,
there
that's a great question. So actually, we didn't look for superconductivity because not for any specific reason, mostly because I thought that the magnetic order would be more likely. And I think it's superconductivity relies on the electron photon coupling. I don't know how large that is. And so I kind of want to stay away from that. But I think we might circle back around and try to see if there's any type of interesting superconductivity that can result, especially because of this spin momentum locking on the surface of the TI. What type of spin pairing would you need, and what type of superconducting pairing would accompany that? I think that's an interesting question. Yeah.
Thanks.
Sure. Anyone
My
ask
turn?
a question? Yeah.
Thank you, Jennifer, for the nice talk. So I'm an experimentalist. I'm interested in the experimentally have people found like interesting results on the patent dielectric approach. You mentioned like Correlated had a paper years ago.
Yeah, so I think what they observed in Corey's paper is the appearance of these satellite peaks. And so it's actually kind of similar to this. When you apply a superlattice potential to the Dirac cone in graphene, it's very similar to the TI Dirac cone, and you end up folding the Brillouin zone. And every time you fold it, the thing is, bands cross at the corners of the Brillouin zone, but they're protected. In this case, they're protected by time reversal. In graphene, they're protected by something else. You don't open up gaps, so you don't get a gapped flat band. You get these crossing points that actually are mini Dirac cones. That's what they call the satellite cones. So in Corey's paper, what they measure is they can actually measure these dips in the density of states. I think they do it by transport. And that is kind of a signature that your potential is having an effect on the Dirac cone. That's the thing that they measure. They don't see any interaction driven effects that I don't remember them seeing anything like that. It's just a question of, can we impose a superlattice potential on graphene, and how do we measure it? And they measure it by measuring these dips in the density of states.
But from the theoretical point of view, so you think that by designing the periodic pattern dielectric and the dual gating, basically we can achieve similar things, right, as using twisted structure.
Yeah, so I think it's I think it's similar and different. So the thing that's similar is that you create this large scale super lattice and you fold the Brillouin zone a lot, and that band folding changes your Dirac cone velocity. The thing that's different is that if you apply a super lattice potential either to this system or in graphene, you only have one Dirac cone. I mean, graphene has two Dirac cones, but they're far apart. So we just talk about one valley. So the super lattice potential is acting on one Dirac cone. So you don't get a flat band. As opposed to in bilayer graphene, you have these two Dirac cones. When you twist them, they can interplay with each other. And that interference is kind of what opens this gap. So it's similar and different. And for that reason, I would expect to see different things. But I bet that in monolayer graphene with a super lattice potential, I bet you still have those Van Hove singularities. And so you could ask, what's the instability in graphene that you would expect? I don't know, it's probably either a charge density wave or some type of magnetism. And if they went up to that 2/3 filling, maybe then that's where they could look for an instability.
Okay, great, thank you.
Yeah.
Jennifer, I have two quick questions. Since we are on this slide, so you mentioned that this satellite Dirac cone, and what about the chirality of the satellite Dirac cone as compared to the primary Dirac cone? Are they opposite to that primary one?
I guess what I think, so I think that there is kind of a conservation law, which would be, so you can get a chirality if you have enough symmetry by winding around the Dirac cone. And as you move around in energy, that probably has to be maintained. So I think that there's some kind of sum rule for all the Dirac cones that are at similar energies. They probably need to sum up to the same chirality, but I don't think that individually they would be constrained beyond that.
Okay, thanks. And my second question is the Van Hove singularity. Does the hexagonal warping has any effect on the Van Hove singularity?
That is a great question. So we actually, we didn't, that is the other next thing that we want to do. So we just considered so far, we went back to the simple model of a linear Dirac cone on the surface and, and then compute this revised band structure with this super lattice potential. But we actually did not include hexagonal warping. And I think hexagonal warping is going to be important because it actually changes symmetry a lot. Well, I don't know about a lot, but it changes the symmetry on the surface. And also we're looking up at 2/3 filling, and that's where hexagonal warping, the higher up you are in energy, the more pronounced the hexagonal warping will be. So one of the next things that we want to do is to include the hexagonal warping and see how does it change like this phase diagram. Does it make this shrink? Does it make it get bigger? How does it change the phase diagram? How does it change the critical temperature? And then the other thing is the anomalous Hall effect is actually, we don't predict that it would be present for the current order. This Miron lattice preserves a lot of symmetry. And in particular, it preserves this, it breaks time reversal, but it preserves the combination of twofold rotation and time reversal. And that combination, I think, makes the anomalous Hall effect vanish. But hexagonal warping breaks the twofold rotation symmetry. So I think that hexagonal warping means that there might be a finite anomalous Hall effect. It's not quantized because this surface is gapless. But I think the hexagonal warping could give you anomalous Hall, and that would be like the easiest thing to probably measure here.
Okay, thanks. I don't see any other questions from the audience. So let's thank our speaker again.
Yeah, thanks for having me, and thanks for the questions.
Thank you very much, Jennifer, for your virtual visit. Have a great day.
Yeah, same to you.
Bye.